Okay, so we ended last class session talking about thermochemical stoichiometry, where we calculated the delta H, right? Now today we're going to be talking about something called Hess's Law. And so Hess's Law basically tells us that if a reaction is carried out in multiple steps, the delta H equals the sum of the enthalpy changes. Okay, now that's a lot of words and it's kind of confusing, but we'll do 6.18 together and it'll help us kind of understand what Hess's law is. So if you guys notice, there are two different equations here, right? We have CH4 plus O2 produces CO2 and H2O gas. And then also it says that if we have H2O gas and H2O liquid, this is the equation for it. Now, if you guys take a look at this equation, it's basically asking what is the delta H for this reaction right here. Now, it looks very similar to this one right here, but it's a little different because the first one up here is H2O gas, and this one is H2O liquid, right? And so we can't assume it has the same delta H as this because remember, it depends on the state of matter. Yeah, what's up, great? Yeah, that's just what is it? Thermochem stoichiometry. Okay, so what we're gonna do instead is we're gonna have to, like it says here, we're gonna have to find the sum of the enthalpy changes. So if you guys notice, we have CH4 and O2, CH4 and O2, and on the right side we have CO2. So it's very similar to this first equation. The only difference is that we need to change the H2O gas into H2O liquid. So basically what we're going to be doing is we're going to be combining these two equations together, okay? And it's a lot easier than it sounds. So you can think of it this way. So if we have this original reaction, CH4 plus 2O2 produces CO2 plus 2H2O. I'm just going to specify that H2O is a gas, and so I'm going to leave it like that. Now, this is the first equation. What we need to do now is we need to take this 2H2O, so I'm just basically gonna transplant it right here. I'm gonna take that 2H2O gas and I'm going to turn it into a liquid. Okay, so 2H2O liquid. Okay, and it's just the reaction right here. So the first reaction and the second reaction. So what happens is I basically turn this, the H2O gas, into the H2O liquid. So this basically cancels out with itself. Does that make sense? We're taking the first reaction, right, where it had H2O gas, and then we're taking that product and then we're turning it into H2O liquid. So since this is the new reactant, since it's the new reactant for the second equation right here, we basically can cancel it out. And then now what do we have? We don't have H2O gas anymore. We have H2O liquid. Okay, so basically we're combining these two equations, we're combining these steps. We said that the first delta H is equal to negative 802 kilojoules, and then the second delta H is equal to negative 88 kilojoules. And so what we're gonna do is since we took this and turned it into this, this is basically the second equation that occurred. The delta H for this equation is basically gonna be the sum. So we just need to add this together. So we're gonna do 802 plus 88, and that should give us negative 890 kilojoules. And that's how you do it. So the delta H for this equation right here is going to be equal to negative 890 kilojoules. It's just the sum. We just need to add up the delta H's of the reactions you need to make it happen. Okay, so basically, it's kind of like a puzzle. You're gonna see a couple questions like this on the AP test. Basically, you'll have sometimes 3 or 4 equations like this, and you just need to get rid of the stuff you don't want on the left and the right until you get the equation that they're asking for. Okay. So I'll do another one with you guys, but that's basically the gist of it. Any questions on that? Make sense? Okay, for sure. All right, let's move down to 6.19. So if you guys want to scroll down, I'll leave this up here for just another second so that people can copy it down. But let's go to 6.19. That's the one that we're going to be doing next. Bless you. All right, so 6.19. Like I said, sometimes you're going to have multiple equations. You're going to have 3 equations. Now, just think of it this way. When you combine all 3 of these, you want NO2 gas, or sorry, N2O gas and NO2 gas on the left. Okay, no matter what, you want to have both of them on the left. And you want to have 3 separate moles of NO on the right side. So if you guys want to try this on your own, just kind of figure it out, feel free to do that, but I'm going to take it step by step. So let's start with N2O, okay? You want to make sure N2O ends up on the left side. So if we look at these equations, numbers 1, 2, and 3, which one of these equations has N2O? Yeah, the third one, right? So the third one has N2O. And so we're going to be using this. So we're going to take equation number 3, and I'm just going to write it. And I want to make sure that N2O is on the left side, because for the final reaction, the one that we're looking for right here, we have N2O on the left side, okay? And then the delta H, the delta H is negative 163.2 kilojoules. Okay, so that is the equation that has N2O. Now we're going to look for NO2 now. Okay, so NO2. Which one of these equations has NO2? Yeah, the second one. This one has NO2. Now, there's a problem though. Okay, we said we want NO2 on the left side, right? But which side is NO2 on this side? The right side. So you're going to have to flip the equation, but if you flip the equation, what happens to the delta H? Yeah, it's the opposite sign. You have to turn it from negative into positive. So I'm going to flip the equation, which means I'll put the product. So 2NO2 on the left side. So I'm just going to take this on the left, and now I'm going to put what was originally on the left, and we're going to put it on the right side. So 2NO plus O2. And for the delta H, we have to change the sign. So we go from negative 113 to positive 113 kilojoules. Okay, so again, it's kind of like a puzzle. You just want to adjust things so that everything ends up on the correct side. Okay. All right, so what we can do now is we can start combining some things together. Okay, so if we combine this reaction together, and I just add it all up. If I add it together, I have 2 N2Os on the left side and 2 NO2s on the left side as well, right? Because these are the only 2 things that are on the reactant side. Okay. Now on the product side, we're going to have 2 N2s, right? We're going to have 2 NOs, and we're going to have how many O2s? 2, yeah, because there's a 1 here and there's a 1 here. So we're going to have 2 O2s. All right. So far, so good? Okay, so the left side looks okay. The numbers are different, but we can worry about that later. But we have the chemicals that we want on the left side. But if you look on the right side, we have a bunch of stuff that we don't want, right? We have N2 and we have O2. But if you look at the equation here, we only want NO. And so this is where we're going to use the first equation. Okay, so we're going to use the first equation. Now, we said that if we have something on the opposite side, they can cancel out with each other. So if we take a look at this, we want to get rid of N2 on the product side, right? So we're going to make sure that there's an N2 on the reactant side. So this is where equation number 1 is. I'm just going to copy it down. Okay. Because if I have N2 here, it can cancel out with the N2 here. And if I have O2 here, it can cancel out with the O2 here, right? Because we can take these and run this reaction and get rid of N2 and O2. Okay. But there is a problem. The problem is there's 2 N2s, right? And there's 2 O2s, but there's only 1 and 1 here. Okay, so what we can do is we can multiply this entire equation by 2. We can double the reaction. So if I put a 2 in front of this, a 2 in front of this, and change this into a 4, and then obviously you're going to have to double the enthalpy as well. So 180.7 kilojoules, and then we'll multiply that by 2. Okay. If I do that, then I have just enough N2s to cancel out the N2 here. I have just enough O2s to cancel out the O2 here, and then I will have 4 NOs. Okay. Okay, and make sure when you do this that you double the enthalpy, because you did double the reaction. Okay, so let's put everything together. Okay. So on the left side, the only thing I have left is 2 N2O, and I have 2 NO2s because the N2 and the O2 canceled out. And on the right side, I'm going to have 6 NOs. Does that make sense, guys? I know it's a lot of stuff at one time, but basically, you just kind of cancel out the stuff on the right side with the things on the left. Okay, and then let's actually calculate the delta H right here. Okay, so we're going to have to just take the sum. We're going to add up all the delta H's for the reactions that we use. Okay, so we have, what is it? Negative 163, so 163.2. Got to make sure it's negative. We're going to add that with 113.1. And then it looks like we had 106 or 180.7 2 times. So we're going to add 180.7 2 times. And so the enthalpy of this reaction right now is 311.3 kilojoules. Let me just make sure I have the right answer. Okay. All right, so far so good, guys? Okay. So what we want to do, now is make sure this equation at the very bottom is the same as the equation right here. Now, if you look at it, it's not the same yet, right? What's wrong with it? Yeah, it's double this, the one that we're looking for, right? Because we only want 1 N2O, but we have 2. We only want 1 NO2, but we have 2. And we only want 3 NOs, but we have 6. So what do we have to do in order to make it the same? Yeah, so we're going to divide everything by 2. So if we divide the reaction by 2, that means we're also going to have to divide the enthalpy by 2. So we can get rid of the 2 here, the 2 here, the 6 becomes a 3 because it becomes halved. And that means the enthalpy, we need to divide that value by 2 as well. So we're going to divide that by 2. And so our final answer, the enthalpy for this reaction right here is going to be 155.65 kilojoules. So the delta H for this guy right here is equal to 155.65 kJ. Okay, and that is our final answer. Kind of hard, huh? A little bit tricky. Yeah, so for these ones, I really recommend make sure you guys do the practice problems, go through a lot of examples of this, go on YouTube, watch people do the problems, try it on your own. Just because for this, you really just need to get a lot of practice in. Like I can go over as many practice problems with you as possible, but you really need to put in the work because you've got to be able to see these patterns on your own, okay? And usually there's at least 1 or 2 of these on the AP test. Yeah, what's up? So we, what we did was we had 2 NO2 right here, which was equation number 3, right? And so the delta H was 163.2. Okay. This one was equation 2, and it was negative 113.1, but we had to flip it, right? Because I needed to take the NO2 and put it on the left side. When you flip an equation, you have to make it the opposite sign. So it was negative, so it became positive. Okay, and then we had this one right here. Oh, sorry, this one right here, 180.7, but we had to double everything to cancel it out. So we doubled 180.7, and then we added it all up. When you add it all up, you should get 311.3. And then I had to divide it by 2 because earlier, remember, we had 2's, 2, 2, and 6. And so we have to have the reaction. So we have to have the enthalpy as well. Yeah, but then you have to add it with 113.1 and negative 163.2. Hey, Mr. Pepper.
Oh man, I love it. Thermal, huh?
Uh-huh. It's hot like you.
Oh, stop it.
All right. So there are a couple examples like this on your homework. So if you guys want to check your answers for that after you guys do it, or if you want any help, I'm actually going to try to leave some time at the end of the class, maybe so we could do a couple types of practice problems you guys need help with. So this might be one of the ones we can go over, okay? So let's move on. We're going to talk more about enthalpy, but this time we're going to be talking about something called enthalpies of formation, okay? Okay, so there's so many different types of enthalpy, but standard enthalpy of formation, and even the symbol is very confusing because it's delta H, right? So change in the enthalpy, it has this circle, which means standard of formation. Okay, so very confusing symbol, and unfortunately, you have to get familiar with what all these symbols are. But the standard enthalpy of formation is just a change in enthalpy, right? Change because it's the triangle delta in enthalpy, which is H, for the formation, which is going to be the F, for 1 mole of a substance from the most stable form of its constituent elements. Okay, now that is a very long, kind of confusing definition. So I kind of wrote this simplified version for you right here. It's basically when you take the elements in the standard state and you turn it into 1 mole of whatever compound, whatever substance you're looking at. And that's the delta H of formation. Okay. It's when you're trying to make a chemical and then how much energy is produced or used in order to make it from its elements, the elements that make up that compound. Okay, so we have a couple examples underneath. Okay, so we're going to be talking about right here the enthalpy of formation for CO2, okay, carbon dioxide. Carbon dioxide, if you guys notice, is made out of carbon and it's made out of oxygen, right? So basically, the enthalpy of formation is telling us how much energy is used or produced in order to make CO2 from its most stable forms of the elements that make it up. So for carbon, the most stable form of carbon is a solid called graphite. It's the stuff that's at the end of your pencils. Okay. The most stable form of oxygen is oxygen gas, O2 gas. So C plus O2 makes CO2. And then the enthalpy of formation is going to be right here, negative 393.5 per mole. Okay, so that's what the enthalpy of formation is. Just how much energy is used or produced when you take the most stable forms of the elements that make up a molecule to make that specific molecule. Okay. That makes sense, Mr. Kupik?
I love the way you explained it.
Oh,
so
thank
is
you.
energy released with the carbon dioxide, or is it absorbed to make the carbon dioxide?
I'm not
That's where
sure.
I'm a little confused.
I'm not sure. What do you guys think?
You
Is
guys know, is energy released or absorbed when you make carbon dioxide? Raise your hand if you think you know. I won't call on you.
I'll call on you,
Who
Josh.
doesn't know for sure?
What do you
Who's
think,
like, I have
Josh?
no idea.
I think it's released.
Why do you think it's released?
Because it's a negative number, so it's gonna be on the product side, meaning that it wasn't energy output.
Exactly. Yes, it is. It is released because it is a negative sign. Energy is released into the surroundings. Good. So if you see a negative sign on the enthalpy change, we talked about this last time.
I was here for that.
Yeah.
That's
Were
how
you?
I knew they knew the answer.
Oh, dude, you know them better than me. I didn't know that.
No, but you said this last time.
Did I?
Yeah. If it's negative, you're losing things.
Sometimes I think I'm just making this up as I go.
-8 cookies means you're losing cookies.
No.
-8 energies means you're losing that much energy.
I don't want to lose cookies.
Yeah.
Anyway, yeah, somebody tries to steal my cookies, dude. Guys, I was a fat kid in elementary. There's no more. Yeah. It's because I love sweets. I killed a dozen Krispy Kreme the other week.
Oh, I thought you
By myself.
Wait a minute.
The first thing I told my wife on our first date is that I don't share dessert.
Nice,
Yeah. That's why I'm such a sweet guy, because you are what you eat.
nice.
Elaine, why are you laughing at me? You don't think I'm sweet?
No, it's true.
All right. I'm also a cheesy guy because I eat a lot of cheese. Anyway, so another example would be H2O, right? H2O is made out of hydrogen and oxygen. And so the most stable form of hydrogen is hydrogen gas, H2 gas. The most stable form of oxygen is oxygen gas. And we have a 1/2 here because remember, for enthalpy of formation, we're talking about 1 mole of the product. So obviously in real life, you can't have half a oxygen molecule. We can have half a mole of oxygen, but that's why we have the 1/2 there. And the enthalpy of formation is negative 285.8 kilojoules per mole.
Are there any delta H formations that are positive that actually absorb energy?
What do you think, Mr. Pepper? You're the
Yeah, I
smarter
already
one.
know, I already know. I
You're the
already
smarter one.
know.
Can't put me on the spot like that.
Ammonia is gonna come up.
Yeah, I don't know. I told you I'm just making this up.
Oh.
Yes, there are positive ones. Okay, and then last one is the formation of oxygen gas. Well, earlier we said the most stable form of oxygen is oxygen gas. So if you're trying to make a chemical that's already the most stable form, right? You're not doing a reaction, right? Because oxygen gas is only made of oxygen. So if the most stable form of oxygen is oxygen gas, you're not running a reaction. So the delta H for a compound that's already the most stable form is going to be 0.
All elements.
All elements as well,
So,
yes.
No, I think that's what it is. It's all elements.
The elemental form, yeah, yeah.
All elements have a delta H.
yes.
I haven't done this for, you know how long this has been? I mean, this is a good review. I haven't done this for, God, 6 years, dude.
Really?
Yeah, I mean, we never get there.
Oh my goodness.
Maybe 5 years. Remember the last time I taught it was.
It's okay, Pepe. I haven't done it in 7 years.
Yeah, exactly. Seriously,
Just
I
need to
was in
one-up you.
college, dude.
All right, so you guys don't need to memorize this. I put a star. If you look on Appendix C of our textbook, you'll be able to see the enthalpy of formation for a bunch of different compounds. So you guys don't need to memorize this. Just know what it means, how to get it. And so we actually have a small table underneath right here where I give you some examples. So these are a bunch of different compounds, and this is the enthalpy of formation of each of them. Okay.
Kill that guy. Kill that guy. She's good at this video.
Yeah.
That's pretty impressive.
Nice. What are you playing? Dude, why aren't you killing him, Elaine? Kill that guy. Dude, Pepik is such.
Elaine's like, what just happened?
Dude, Pepik, you're such a snitch, man.
She had to do that all the way down the lecture. I was very disappointed.
Okay. Alrighty, guys. So what we're gonna do now is we're gonna go through a couple of examples, and we're gonna see, hey, is this going to be an equation that represents the standard enthalpy of formation? Okay. So let's go through each example. So we'll look at number A, reaction A first. So I'm gonna cover up the other ones just so that you guys are not distracted. But let's start with number A. Okay, so we are trying to find or see if this reaction right here represents the enthalpy of formation for Na2O. So Na2O is made out of Na, and it's also made of oxygen. So what you need to do is you want to look on the left side and see if those are the standard forms of each of those constituent elements. So let's look at sodium. Okay, it says that sodium is a solid. So is sodium right here in elemental form? Is this the most basic form you can get of it?
Yes.
Yes, this is the most basic form of sodium you can get. It's just a solid sodium piece of metal. Okay. Okay, the other element is oxygen. Now, if we take a look at oxygen, is O2 gas the most basic form of oxygen that we can get? Yes, we just said that above, O2 gas. So since both of them are yes, they are both the most standard, the most simple elemental form of the things that make up this chemical that we can get, is this going to represent the delta H of formation of Na2O? Yes. Okay, so this reaction is a yes. It does represent the most basic form because both of them is in the proper state of matter. Okay. So I know some of these we haven't gone over all of them, right? Like we haven't gone over sodium, but we did talk about it in redox that the metals, you want them in the standard solid form. So let's try equation 2 now. Okay, so I'll give you guys a minute to try this with the person next to you. We have KC, we're making a KCl. And so I want you guys to take a look at the equation and figure out, does this represent the delta H of formation, the standard state? Elaine, is he dying?
Say, chess.
Oh, really? Nice. I used to sleep when my teachers talked. So that's why when I have bad students now, it's like, I deserve this. I deserve it. Yeah, what's up? Yeah, Appendix C. It's at the very back of the textbook. Yeah, Appendix C. The one online. We just use the one on that's on Canvas. Yeah, what up?
So typically, metals supposed to be solid.
Typically, yeah, there's some exceptions like mercury. Remember, mercury is the only metal that's liquid at room temperature. So yeah, that would be different. Yeah, so like oxygen is a non-metal, chlorine is a non-metal. Metalloids, yes, you will. And those ones, you'll usually have a reference sheet to look back to. Yeah, like some things like are obvious, like silicon, but if you look lower, like antimony. Yeah, like we just don't know that right off the top of our head. So you'll always have an appendix. You don't have to memorize what the standard state is. Okay. Okay, so let's go over B. So KCl is made out of potassium and chlorine. And so let's see if the stuff on the left side represents the standard state. Okay. So potassium, is this in its most basic form? No, why not?
Because it's a liquid, not a solid.
Yes, if you guys notice, it's a liquid, but we said that metals have to be in solid form. So right off the bat, we already know that the delta H of this, oops, I flipped those around, is not going to be the enthalpy of formation, the standard enthalpy. And it's because K is not solid. Okay, it's in liquid form. We want the metal in solid form. Okay, but Cl2 right here, it is in its most basic form. Cl is a diatomic gas, so it wants to exist as Cl2 gas. Okay, so just be careful about those.
So did you say that one was?
It is not
Okay, that's not making one more.
that too. I just mentioned that K is,
Oh, solid.
yeah, it's liquid. It needs to be solid. But yes, Mr. Pepik is right too. See, this is why I need you, Mr. Pepik. Okay, it's also because it's making 2 moles. It needs to make 1 mole.
I didn't see that.
See this, we complete each other. Okay, all right. And then last but not least, guys, we're gonna be taking a look at this one. I'll give you guys another minute to try C. I want you guys to see, yes or no, does this reaction represent the standard enthalpy of formation? Okay. This one should be kind of easy. Okay, just remember the definition of standard enthalpy of formation. It's you're trying to produce something very specific. Why are you taking her away from me?
Just the response to this.
I know. You just stole my TA. Perfect steals all my things. You stole my, dude, you knew exactly what I was gonna say. I was gonna say that. Pepik did steal my heart. Pepik, when he walked in and that light was shining off the baldness of his head, that's when I knew. Pepik had stolen my heart. Anyway, okay, so let's go over C. This one should be pretty. Yes or no? Does this represent enthalpy of formation? No. Okay, there's a lot of reasons why. Okay, so anyone want to give one reason why it does not?
Diamond.
Okay, so yeah, we'll start. We'll raise our hands. But yeah, diamond. Carbon's most basic form is not diamond. We said earlier that it was graphite, right? So that's automatically one reason why it's not. Great. Did you have a? Okay. Anyone else got another one? Yeah. Exactly. The standard states are where? They're on the product side, right? And so we need to have these on the left side. So if you guys remember the definition of standard enthalpy of formation, it's when you're trying to make 1 mole of a specific product, right? But here, where is the product that the 1 mole? It's on the left side, right? We want to have that on the right side. So yeah, this would have to be the reverse equation. We would have to reverse this equation right here in order to have it. Yeah.
Was there the other elements besides carbon that have a different graphite type?
Yes, there are. Okay. Alrighty, so we're gonna take a quick 5-minute break if you guys need to go to the restroom or anything, and then we're gonna get into the last topic for today. Make sure you guys stay on Canvas, especially keep an eye on this chart right here because we will be using this chart for the next type of questions that we're gonna go over. So take about 5 minutes, and then we'll come back together and finish it up for today. Now, like I said, you're gonna need access to this table right here. So I highly recommend as we're going over the problems that you just have this open on your phone or your Chromebook, and you can just look at the problem up here. I'll kind of zoom in just so that we can take a better look at the problems that are on the screen. But you will need access to this table right here. So just keep that in mind, okay? Okay, so we said earlier that we can find that different compounds that they have different enthalpies of formation, right? So they all have, you can kind of think of this as like the energy that is inside of them, okay? Now, if I want to find the energy, the enthalpy change of a reaction, okay, this big ugly symbol basically just means you're just gonna add up all the energies of the products, and then you're going to subtract from that all the energy of formation of the reactants, okay? So that's basically what that equation means. If I want to find the delta H of a reaction, you want to add up all the energies of the products and subtract all the energies of the reactants. That's what that sigma sign, that Greek symbol means. Okay, so we'll do an example just so that you guys have something to go off of. And then after that, I'll have you try one more on your own. And then after that, we'll go over some practice problems with Hess's Law, okay? Okay, so here this question is asking us to find the delta H of the reaction for the combustion of 1 mole of glucose. This is glucose right here. You might have seen it in biology, to carbon dioxide and H2O. So what we're gonna do is if we want to find the delta H of the reaction, you're gonna want to add up the energies of the products, okay? So whatever the energy of CO2 is, whatever the energy of H2O is, and then you want to subtract the energy of the reactants, okay? So what you're gonna do is you're gonna just subtract the products minus the reactants, okay? And it's also going to depend on how many moles of each there are. So you're gonna have to multiply carbon dioxide by 6, and then H2O by 6, and et cetera, okay? Yeah, what's up?
Because it's glucose, right?
Yes.
Can we just assume that it's already, oh, I know, like, for this one, it's really specific, but can we assume that it's something positive because glucose would be converted to?
I don't know, we're about to calculate that. Well, you're wrong, it's not positive. It's okay. It was a good reasoning. All right. So let's figure out the values for all these compounds first, and then we will try out the problem. Okay, so let's go back to that table. Okay, what is the enthalpy of formation for glucose according to this? Yeah, so if you take a look at it, it's what? Negative 1273. You guys see it at the very bottom right here? Okay, so it's going to be negative 1273. So we're just going to go down to the problem. Oops. And then we're going to write that, hey, for glucose, the energy is going to be negative 1273. Okay, so I'm going to write that glucose, negative 1273. Okay, obviously that's in kilojoules per mole. Okay, now oxygen, we don't need to look this up on the table because this is elemental form, right? So what's going to be the enthalpy of formation for oxygen? 0, yes, correct. Okay, so oxygen is going to be 0. Okay, so far so good? Okay, and again, all these numbers will usually be provided for you. They're in the appendix, and that's how you'll find them for your homework. Okay, now let's go to CO2. So if we look at CO2, what's the enthalpy of formation for carbon dioxide? Yeah, negative 393.5. So we're going to go negative 393.5. Negative 393.5. And then lastly, we have water. Now, if you guys look on your chart, we don't have one for water, right? Okay, we don't have water. But if we go up a little bit more, we do have one for water. What's the enthalpy of formation? Yeah, negative 285.8. Okay, so again, you don't need to memorize all these. They'll be provided for you. But just know how to use them in order to find the enthalpy of the reaction. Okay, before we solve this problem, any questions on where we got the numbers from? Just Appendix C. Okay, go to Appendix C and you'll find all of these in there. Just make sure you're careful about the state of matter, solid, liquid, gas, things like that. Yeah. So there's gonna be slight variations in the numbers. It won't be anything crazy where it'll change your answers and make you go wrong. But I do recommend learning how to use the appendix because they'll list like solid, liquid, gas, and you need to determine which one you want to use. It is a little bit annoying, but I do recommend that you use that. Okay, so let's calculate for the delta H of the reaction. Okay, so what we're gonna want to do is we're gonna look at the products first. Okay, so what we're going to do is we're going to add up all of the products. So we have carbon dioxide, which is negative 393.5 per mole, right? How many moles of carbon dioxide do we have though? Yeah, so for this equation, you're going to do 6 times negative 393.5. Okay. And then we're going to combine that with 6 moles of hydrogen, or not hydrogen, water. And so we're going to have negative 285.8. Okay. And so this is going to represent the value for the products. Okay. God bless you. That's going to be this thing right here. Okay. So this symbol right here for the equation is basically just telling you, hey, add up the enthalpies for the products. Okay. Okay. And then it tells us that we are going to subtract it. So we are going to subtract it with the same thing, the energy of the reactants. Now, if you guys take a look at this, we have 1 mole of glucose. So we're going to have negative 1273. And then we're going to combine that with oxygen, or O2, but it's going to be 0. So 6 times 0, which is going to be 0. So this would be the full equation. I know I wrote it out really big, but basically that is how you are going to calculate the enthalpy of the reaction. Okay. All right, so I'm going to give you guys a minute. Let's see how good you guys are with your calculators. So try that out. Let's see what answer you get. You can double check with the person next to you. If the way that I wrote it is a little bit confusing, you can write it however you want and calculate however you want. Just be very, very careful with the positive and negative signs because that will trip you up. I know. Science is all math, unfortunately. I think so. Do you guys know the story of calculus? Where it came from? It's so badass. So like Isaac Newton invented calculus because he's like, hey, I'm trying to do physics, but algebra is just not cutting it. So I'm gonna make my own system of math, and that's where calculus came from. That's so badass.
I think he got hit in the head way too hard.
Maybe he did by that apple, but dude, that's crazy. How do you invent your own system of math? Because what exists is not cutting it.
That's ridiculous.
Yeah, gangster, dude. All right, so let's finish up this problem. So I'm gonna give you the final answer before I actually start solving it out. But for the final answer, the heat of reaction, you should have gotten negative 2802.8 kilojoules. Okay, so something close to that. Okay, so let's go through the calculations. For the products, you're gonna multiply the 393. Oh, my goodness, my fingers are so fat. Okay, we're gonna multiply the 393.5 negative by 6. Okay, and we're gonna combine that with 6 times negative 285.8. So let me actually write that down. So this value right here is gonna be negative 2361. Okay, and then for this one, you're gonna do 6 times 285.8. And it has to be negative, but it will be negative 1714.8. So if you add these together, what you should get is 4,000 negative 4,075.8. Okay, and I'll do that one in blue. Negative 4,075.8. Okay, obviously right here, the 6 times 0 is going to be 0. And then we're going to be subtracting it by negative 1273. And so negative times negative is going to be positive. So you're going to end up adding to this. So you're going to add 1273 and you should get 2802.8. And so that's where you get that number from. Okay, so hopefully that wasn't too bad. A lot of it is just calculations, just making sure you're clear with the positives and negatives and just being very careful. Okay, which is not conducive for the time limit on the AP test because you got to go fast, but you also want to double check your work. So a lot of practice is probably needed for this. Okay, so speaking of practice, let's go to 6.23. I'm going to give you guys the next maybe 4 or 5 minutes to try that out on your own. You can work with the person next to you. After that, we're going to go over the answer together. And yeah. And then we'll just go over some practice problems for the rest of the day. We'll be all done. So we're going to go over 6.23. I just want to make sure that you guys have all the values that you need on that table. You do. Okay. So yeah, try 6.23. Everything that you need is on the table, and I'll keep this up here as an example. Okay. Dang, there's a Hess's Law calculator. This is crazy, man. There is. Y'all know Wolfram Alpha? Wolfram Alpha? It's this crazy monster calculator that's online. Help me pass college, dude. Wolfram Alpha. Bless you. guys, I'll give you another minute to finish up. Alrighty, guys, let's go over 6.23, and then we will finish up with some Hess's Law practice problems. I found a bunch online that we can suffer together going through. Some of the numbers look really big, which will be exciting. Okay, I'm sure you guys will all be happy to do those. All right, so 6.23. So if you guys take a look at this, very important to notice one thing before we start. How many moles are we looking at? Yeah, we're looking at 2 moles of ethanol. Okay, so just keep that in mind. Okay, now let's get started. So what we want to do is find the enthalpy for all the reactants and products. So I'm just going to go down the line and ask you guys what the enthalpy for all of them are. So ethanol, what is the enthalpy of formation of that? Is it negative 200? That was positive. I might have remembered it wrong. Yes, negative 277.7. Okay, so we're going to start. Let me go down a little more. Okay, so we're going to start with negative 277.7 kilo. My goodness, I could not. Sorry, guys. So this is what I said. My brain got dull too. 277.7. Thank you. Okay. What about oxygen? Yeah, this is 0 because it's an elemental form. Now, CO2 and water, same thing as before. We got negative 393.5. And for water, we got negative 285.8. Okay, everyone got those? Hopefully the same. 3 of them were exactly the same as last time. But then again, I goofed on the ethanol one, so I guess it's not too easy then. Okay, so we're going to take all the products and the reactants, and that's going to give us our value for the delta H of reaction. Okay, so we're going to take our products, and so we have 2 moles of carbon dioxide, so 2 times negative 393.5. We got 3 moles of negative 285.8, and then we are going to subtract from that the reactants, which is going to be 1 mole of ethanol, which is 277.7, and then we're going to combine that with 3 moles of oxygen, which is 0. Okay, so we can kind of just ignore this right here, and this back part will basically just turn into plus 277.7. Okay, so we just need to find the enthalpies for the reactants, and so we're just going to do 2 times 393.5, and that'll get us to negative 787, so negative 787, and we're going to combine that with 3 times 285.8, which will get us to negative 857.4. Okay. All right, so we just want to add all the products together, so we'll add that with 782. And just make sure that one is negative, and then we just need to add 277. I messed up. Sorry, guys. So 282 plus. Wait, what's wrong? Sorry. Did I really? Thank you, guys. You guys just teach this class at this point. I clearly don't know what I'm doing. 787 and then 857.4. Thank you, guys. And that's going to be negative 1644.4. And then we're gonna add 277.7. That'll give us negative 1366.7. Am I right? Okay, so just want to make sure, because clearly I'm figuring this out as we go. Okay, so one thing before we finish, if we look at the units for this number, what are the units for this number? Look at the table. What's the units for the enthalpy of, yeah, kilojoules per mole. Okay, if you look at the table, where all the stuff is, it's gonna be kilojoules per mole. Now, so we have kilojoules per mole. So if it's per mole, how many moles is it talking about? 1. But in the question, what are we looking for? 2 moles. So what do we need to do in order to turn it into kilojoules per 2 moles? Got to multiply it by 2. So we're going to have to multiply it by 2, and that will finally give us the answer, which is going to be negative 2733.4 kilojoules per 2 moles. And this will be our final answer. Okay, so just make sure you're very careful. It's looking for 2 moles. All right, and that's gonna be it for all the new content for today. We got 2, I guess, very specific types of problems that will be coming up the next time we meet. One of them is gonna be what our lab is based on after Thanksgiving break. And so, yeah, something to look forward to. All right, so we're gonna end the day off by just working on some Hess's Law problems, just because I know that we went through it a little bit quick. I wanna make sure you guys have enough problems to work on. So if you guys are good with that, let's do some Hess's Law problems. Anyone need more time copying this down? Okay. So I found this on Google. It was like the second search. I just literally Googled Hess's Law problems, and you get a bunch of these things. So this is one way I recommend that you guys do practice problems, is by just Googling them, and you'll find a bunch, and that'll really help you out with learning how to do these types of problems, okay? So let's start off with number 1. Oh, I should cover the answer, huh? Oops. Well, even if you have the answer, you got to figure out how to get there, but we'll hide it. No spoilers. Okay, so you want to find the delta H of the reaction below. The PCl5 forms PCl3 and Cl2 gas, and you have those 2 equations right there. I'm going to do the first one with you, and at any point, again, same as usual, if you know how to do it, just ignore me. I know that you guys are kind of sick of my voice by now. I'm sick of mine too, and that way you guys can get some practice in. But if you're still struggling, I'm going to go through it step by step. All right, so what you want to do is you want to make sure that everything in the final reaction is in the correct spots. That's the best way to start off. So PCl5 is on the reactant side. So we look for PCl5, and I see PCl5 right here. So I'm going to copy down the reaction, PCl5, and it's on the left side. So you want to make sure it stays on the left side. And that forms P4 and 10Cl2. And the enthalpy of the reaction is 3438. All right, we want to make sure that PCl3 is going to be on the product side. So if we take a look here, we see that PCl3 is already on the product side. And so we're just going to copy down the equation as is, because PCl3 is on the product side. Okay, so 6Cl2 and then 4PCl3. And the delta H is negative 2439. Okay, so let's just make sure everybody is in the right spot. PCl5 is, we want it on the left side, so we got it on the left side. PCl3 is on the right side, so we got that on the right side. And then Cl2 is on the right side, and it looks like we have Cl2 on the right side and the left side. And so it seems like they're going to be canceling each out a little bit. Okay, so let's do some magic. Okay, so we don't want P4. So if you guys notice, there's P4 on the right side and the left side. So the P4s are going to cancel out. Okay. And then we want to make sure that we cancel out the CLs as well. So if I have 10 CLs on the right, 6 on the left, they're going to cancel each other out, right? But which side will end up with PCl still on that side? Which side will still have Cl2? Yeah, the right side, because it's only going to be canceling out 6 of them. So it's going to change the number from 10 to 4. Okay, because 10 minus 6 is going to be 4. It's only going to be able to get rid of 6 of the Cl's on the right side. So what we can do is we can combine these equations. And so we're going to copy down everything on the left. The only thing on the left that's left over is 4 PCl5. On the right side, we're going to have 4 PCl3 and 4 Cl2. Now we also want to make sure that we find the sum of the enthalpy. So what I'm going to do is I'm going to add those together. So 3438 minus 2439. So the change in enthalpy will be 999. 9. Okay. Now, is this the final answer that we want? 9. It's not. Okay, because what's coefficients do we want in front of all of them? We want them to be 1. So what we're gonna have to do is we're gonna have to divide the entire equation by 4. Okay. So if we divide the entire equation by 4, we're going to be getting rid of the 4 here, 4 here, 4 here. That turns them all into 1. And then we're going to have to divide 999 by 4. That's going to divide that by 4. And that'll give us a final answer of 249.75 kilojoules.
I can't see the board. Did you have to reverse one of those?
No.
Okay, did you have to reverse the top one?
No.
So, I just can't
This is the second equation right here. Yeah. I mean, freaked out, Mr. Peppick.
So what do you do if you have to reverse it?
What do we have to do if we reverse it, guys? Yeah, you opposite sign, switch the signs.
How do you solve it up there? Do you do it beforehand or after?
We switch it first.
But
Yeah.
then you divide after.
Mm-hmm. All right, and then let's make sure we got the right answer, guys, because Mr. O is very unreliable with the numbers. Yeah, pretty much the same. All right, so I'm gonna give you guys a couple minutes now. I'll give you guys about 5 minutes. I want you guys to try number 2. Okay, now the answer is up there, but I'm gonna hide the answer. Okay, so take about 5 minutes. You can work with the person next to you, try to solve that out, and then we'll go over it together. This one is a little bit trickier because we got 3 equations, but same thing. Make sure you guys put the correct compounds on the left and the right sides.
Are these the questions at the end? Is that like that?
No, yes,
These
that's
questions are embedded with that.
right here. This is 1/2 and then 7/2. And then you want 5/2. No, this is I just found one.
Oh, but I'm saying, is it in the, in the notes?
Or no. I just found a link on that. I'll put the link in the notes.
It's not what I think I have some labels. I have labels because I take this.
Oh my goodness. This one's hard. Yeah, the answer's up there if you want to check it. All done. Thank you. Oh. No, I have my eyeballs. Thank you. Alrighty, guys, just another minute, and then we will go over it together. I have the answer up there if you want to check it. No, it's a cough. I have a really weird cough. Told I have a smoker's cough, but I don't smoke. Yeah, I had bronchitis when I was like young, and apparently there's a lot of scar tissue. That's why my cough sounds like that. That's what happens when you get old, guys. Everything's just bad. Alrighty, guys, so just for the sake of time, I'm gonna start going over it. If you're still finishing up, again, feel free to kind of just zone me out and finish it up on your own, but I'm gonna take it step by step, and let's see if we can figure this one out. Okay, this one is kind of tough. All right, so we're gonna make sure, again, that we want the stuff that's on the left to be on the left. So we got CO2 and H2O on the left side, and so if you guys notice, there is CO2 and H2O here, so we want to make sure that they end up on the left side. This is the only equation that has carbon dioxide, and so that's the reason why we want to make sure this is on the left. Now, right here in the equation given, it's on the right side. So what do we need to do to switch the equation around? What happens if we switch the equation around? Yeah, we got to change the sign of the enthalpy, right? So we got to make sure that when we switch it, that it turns positive. Okay, 7/2. And then the delta H is going to be positive 283. Okay, make sure you're very careful about that. Okay, so that's the third equation, and we set it up like that. Now, we want to make sure that the stuff on the right is also on the right. So we want to make sure that C2H2 is also on the right side. Now, if you guys take a look at all this, the only equation with C2H2 is this first one right here. And it looks like we need to switch that around. So just make sure you switch the delta H. So this equation right here is going to flip. We're going to have C2H6 produces C2H2 plus 2H2, and we need to make sure we flip the delta H so that it's 94.5. It's positive. Okay, so we have basically everything we want on the correct sides, but we want to make sure that we use all the equations since we're going to have to use it. Now, if you guys notice on the right side, we only want C2H2 and O2, okay? But if you guys take a look at the equation right now, it looks like H2 is the kind of outlier that's hanging out. We don't want H2 on the right side, so we want to get rid of it. Okay, luckily for us, in the equation we haven't used yet, H2 is on the right side. You guys see that? And so we want to get rid of H2. So we're going to take that equation and we're going to flip it so that we can get H2 on the left side. And then, so we'll have 1/2 O2, and then we'll have H2O, and then we will have delta H. Since we flipped it, we have to turn it negative 71.2. All right, so we're not done. We're not going to start solving this yet, but any questions on why I set up the equations the way that I did? Okay. We want to make sure all the reactants end up on the correct sides and all the products end up on the correct side. The reason we flipped the second equation is because I want to get rid of this H2. Okay. Yeah, what's up? Are you good? Oh, okay. Sure. Any questions? Okay, now the big problem here is H2. Okay, H2 does not even belong in the equation. Okay, so there's no H2 in the final one, so let's get rid of H2. Now, if I want to get rid of both of these H2s, I only have one here. So what do I have to do to this equation on the bottom? You got to double it, right? So we're going to put a 2 in front of the H2. If you double 1/2, it just turns into 1. And we also want to double H2O. But if we do that, we need to double this value right here. And so that's going to turn into 142.4 kilojoules. Okay, so if we do that, we can cancel out the H2s. Okay. And then we're almost ready to go. If you notice, there's a C2H6 here, so that'll cancel out the C2H6 here. Okay, it looks like there's one O2. If it's 7/2 O2, if you guys know, 1 is the same thing as 2/2. So if we get rid of 2 here, we can change this to 5/2, and this O2 will cancel out. And there you go. We're basically ready to solve it. So we're just going to bring down everything that we have. We have 2 CO2. Oh, I forgot to cancel this out. Sorry. So this 2 H2O is going to cancel out this into 1. We're going to make 1 H2O. It looks like we have 1 C2H2, and then we have 5/2 O2. Okay, so for our delta H, we just need to find the sum of those values. So I'm going to take 283 plus 94.5 plus 1, wait, minus, thank you, plus 1, minus 1. Minus 142.4. Thank you guys. Forgot to put the negative sign there. So that'll be negative 235.1, and that'll be our final answer. Okay, so that's how you do Hess's Law. Hopefully those 2 problems were helpful. Again, you have a couple of these on your homework. Do you guys want the link to this website with all these problems? Yeah, okay. I'm gonna put that in the class workbook. So I'll put this up in just a second, but I'm gonna put it right underneath Hess's Law if you want extra practice. So I'll put it right here. Extra practice. Yes. $283 what? 283 plus 94.5 minus 142.4 because it's negative. Okay, so I just put the link to that to this page if you want extra practice. I put it under 6.19. So it's right here if you guys want extra practice. Well, other than that, good job, everybody. Hope you guys have a great weekend, and I'll see you guys on Tuesday.